Okay, so continuation. Actually, this will be the last part or last uh, lecture for momentum transfer. It's all about compressors, no? Fans, blowers, and compressors. These equipments and devices are very important in transporting gases or fluids, okay, which are considered to be compressible. Okay, so fans, blowers, and compressors, these are machines that move and compress gases. Fans discharge large volumes of gas, usually air, into the space or large ducts. They are low-speed machines that generate very low pressures on the order of around 0.04 atmosphere. Blowers are high-speed rotary devices using either positive displacement or centrifugal force that develop a maximum pressure of about 2 atmosphere. While compressors, which are also positive displacement or centrifugal machines, discharge at pressure from 2 atmosphere to several thousand atmosphere. Note that while pump generally refers to a device for moving a liquid, the term air pump and vacuum pump designate machines for compressing a gas. Now, in fans, the density of the fluid does not change appreciably and may be assumed constant. In blowers and compressors, however, the density change is too great to justify assumption, and in discussing these devices, compressible flow theory is required. Okay, let me repeat. Uh, Fans are usually low-speed machine, around 0.04 atm, while blowers are high-speed rotary devices with a maximum pressure of 2 atm. If the pressure is beyond 2 atm, compressor na ginagamit. Okay? Well, almost all of them are positive displacement or centrifugal machines. Now let's discuss fans. Okay? Uh, Fans and blowers generally used for low pressure and high volume requirements. While fans, large fans are usually centrifugal, operating on exactly the same principle as centrifugal pumps. Their impeller blades, however, may be curved forward. This would lead to instability in a pump but not in a fan. Now, typical fan impellers are shown in the figure in the McCabe, and clearances are large and discharge heads low from 5 to 60 inches. Okay. Now, for us to easily understand how to calculate problems referring to centrifugal fans, let's answer this particular problem. A centrifugal fan is used to take flue gas at rest and at a pressure of, so we're given okay, a centrifugal fan is used to take flue gas at rest and at a pressure of 29.0 inch mercury and at a temperature of 200 degree Fahrenheit. That's around 93.3 degrees Celsius. And discharge it at a pressure of, so the discharge pressure is equivalent to 30.1 inch mercury with a velocity of 150 feet per second. Now we're being asked to calculate for, so we are required, okay, for the power needed to move with a volumetric flow rate of 10,000 standard cubic feet per minute. So we're required to move 10,000 standard cubic feet per minute, or CUFM, of gas using standard conditions of STD condition of 29.92 inches mercury and a temperature of 32 degree Fahrenheit. Now the efficiency of the fan is equivalent to 65% with a molecular weight of the gas which is equivalent to 31.3, okay, grams per gram mole or pounds per pound mole. Okay, so we're required to calculate for the power required to move the 10,000 standard cubic feet per minute. So solution, okay, first we have to calculate the actual suction density. And this can be calculated using the formula, okay, density A is equivalent to the ratio of the molecular weight multiplied by the pressure, okay, using standard condition divided by, so we have 31.3 inches mercury multiplied by the quantity 29, which is the pressure, okay, of the centrifugal fan inlet, inches mercury, multiplied by the temperature, okay, which is absolute, so it has to be in Rankine, so 460 plus 32 divided by, of course, the standard, okay, standard conditions of 359 multiplied by 29.92, which is the standard condition of pressure, inches mercury, multiplied by the, of course, 460 plus the temperature of the Fahrenheit, 200 degree Fahrenheit. This will give us 0.0630 pounds per cubic feet. In short, this is just ideal gas law. PV is equivalent to nRT. Then this is the suction density, after which we'll get the discharge density, of course using the discharge pressure all over the inlet pressure for us to be able to obtain the suction, the discharge density. So we have 0.0630 multiplied by the ratio between the discharge pressure all over the suction pressure. So 30.1 divided by 29.0. This is equivalent to 0.0654 pounds per cubic feet. So we already have the suction density and the discharge density. After which, we're gonna have to calculate for the average density of the flowing gas. The average density of the flowing gas is actually equivalent to, of course, 1/2 of the summation of the two density. So we have 1/2 0.0630 plus 0.0654. So this is simply equivalent to 0.0642 pounds per cubic feet. Okay, after that, we calculate for the mass flow rate. Q. And the mass flow rate, of course, we're given, that's 10,000 standard cubic feet per minute. You multiply it with the pressure, or rather the molecular weight, divided by the 359 standard temperature and pressure times 60, so that we can have the value of your mass flow rate. Mass flow rate then is equivalent to 10,000 cubic feet per minute multiplied by 31.3 divided by 359 times 60, which is the conversion for the time. Kasi minutes siya. So this is equivalent to 14.53 pounds per second. Now the developed pressure is actually equivalent to delta P, which is discharge pressure minus the inlet pressure divided by the average density. Okay, this is actually the pressure head. This is then equivalent to 30.1 minus, that's a discharge, minus the inlet, which is 29. Then of course the conversion factor 144 and 14.7 divided by the density, which is 29.92, conversion factor times, of course, what we got, the average 0.0642, leaving us with the answer of 1,212 feet pound force per pound mass. After which we can calculate for the velocity head. Remember the equation for the velocity head, and English yung ginagamit natin. So we have average velocity squared divided by 2gc is equivalent to, so this is BB, discharge, and according to the problem, your B sub B is actually equivalent to 150 feet per second. So 150 feet per second quantity squared divided by 2 multiplied by 32.2 or 32.17. This is actually equivalent to 349.7 feet pound force per pound mass. Okay. Using, of course, the formula, okay, for the Bernoulli's equation, assuming that friction losses, it doesn't affect the system. Okay, why? Because the system in focus is very short. Therefore, our equation will be shaft torque is equivalent to, okay, delta P over density plus delta B squared all over 2gc. Assuming that your initial velocity is 0 and there's no elevation, so your potential head is also 0. and assuming that the flow is turbulent, therefore the value of your alpha or the correction factor for the velocity is also equivalent to 1. Therefore, for us to be able to obtain the shaft work, and your shaft work is actually equivalent to work pump multiplied by the efficiency, we can calculate for the work pump. Work pump then is equivalent to uh, quantity 1212 plus 349.7. This is the uh, pressure head, and this is your velocity head. Okay, you divide this with the efficiency of the pump, which is actually equivalent to 65%. 0.65. The answer then is equivalent to 2,402 feet pound force per pound mass. This is your work, the work of the pump. Okay. And then of course, for us to be able to obtain the power required, simply convert this one to horsepower. So power is equivalent to, okay, the mass flow rate. You multiply this with the calculated work pump divided by the conversion factor of 550. So this will become 14.53, the one that we have calculated already a while ago, multiplied by 2,402 feet-pound force per pound mass. Converting this value to horsepower, so the answer is 63.5 horsepower. So this is the uh, horsepower required to push 10,000 standard cubic feet per minute of air. Okay, so again, most of the problem can be answered using the Bernoulli's equation. Okay, next. Okay, so that is for centrifugal fan. Okay, so again, fan is relatively with a low speed machine. These are low speed machine. Let's proceed with blowers and compressors. For blowers and compressors, we need to consider changes in temperature and pressure. Okay. Now, when the pressure on a compressible fluid is increased adiabatically, which means that there's no exchanges of heat in and out of a system, the temperature of the fluid increases. Okay, so if the pressure increased, the temperature also increases. Remember that adiabatically. The temperature rise has a number of disadvantages. Because the specific volume of the fluid increases with temperature, the work required to compress a pound of fluid is larger, okay, than if the compression were isothermal. Now, excessive temperatures lead to problems with lubricants, stuffing boxes, and materials of construction. Now, the fluid may be one that cannot tolerate high temperatures without decomposing. But for isentropic or adiabatic and frictionless pressure change of an ideal gas, the temperature relation that we have to use will be this equation. The ratio of the discharge temperature all over the input or inlet temperature, okay, is equivalent to the ratio of the discharge pressure all over the inlet pressure. Okay, raised to 1 minus 1 over the ratio of the specific heat, okay, which is Cp all over Cv. Now, we have a number of equations to be used for uh, compressors or compression of gases. Okay, one of which is the changes in work is equivalent to the integral of the change in pressure all over the density, which is actually equivalent to a head in the Bernoulli's equation. Again, remember the different heads of Bernoulli's equation. We have the pressure head, kinetic head, potential head, friction losses, and shaft work. Okay, so for compression, assuming that we are considering only the pipe in and out of a compressor, then we're gonna have to consider that there's no change in the friction losses, so we cancel out the friction losses head. There's no uh, uh, potential head because there's no elevation, assuming that the velocity doesn't affect, so only the pressure head will be equated to the shaft work, which is uh, yung sa compressor. So there are a lot of or a number of conditions to be considered, okay, in compressors. Number one, if we have an adiabatic compression. Okay, for an adiabatic compression, for uncooled units, the fluid follows an isentropic path. Okay, for ideal gases, the relation between pressure and density will be given by this particular equation. We have pressure all over the density raised to the ratio of the specific heat, Cp over Cv, is equivalent to inlet pressure divided by the inlet density raised to the ratio of the specific uh, heat, this one. Okay, and then if we want to obtain the work done by the compressor, simply manipulating this equation will obtain this equation. Okay, now this actually shows the importance of the compression ratio. Compression ratio is actually equivalent to the discharge pressure all over the inlet pressure in a compressor. Okay, now remember that this equation can only be utilized for adiabatic compression. Okay, that is for adiabatic compression. Now, how about for isothermal compression? Okay, so for isothermal compression, this is when cooling during compression is complete, the temperature will be constant, and the process will be isothermal. Therefore, the relationship between the pressure and density will be equated or will be simply equivalent to the ratio of pressure all over the density is equivalent to the inlet pressure all over the inlet density, which is much simpler than the equation if the compression is adiabatic. Okay? Then, of course, there is the polytropic compression. Okay, this one happens in large compressors. The path of the fluid is neither isothermal nor adiabatic. So you'll have to consider a lot of things. The process may still be assumed to be frictionless. However, it is customary to assume that the relationship between pressure and density is given by the equation pressure all over density raised to n, okay, n, is equivalent to PA all over density A raised to n. What is PA? Inlet pressure, and density A is inlet density. Now, the ratio of specific heat will be replaced by the value of n, okay, and N is simply a constant for polytropic compression. Now, in compressors, the equation for obtaining, or the power equation, or the efficiency rather, the compressor efficiency is actually the ratio of the theoretical work to the actual work, which is similar to our equation for the pump. Okay, the work pump multiplied by the efficiency is equivalent to shaft work, remember. Okay, for compressor efficiency, the ratio of the theoretical work to the actual work is, as usual, the efficiency, and it's denoted by the value of N. The maximum efficiency, remember this one, of reciprocating compressors is around 80 to 85%. It can be up to 90% for centrifugal compressors. Now, if you want to calculate for the value or the power compressor, simply utilize this particular equation. Okay? Now, as part of your sheet work, please solve the following problems. Okay? Together with our sheet work. Okay, sunod-sunod lang yan. Just answer the following problems. Okay, I have uploaded these questions already in your BBL, but all answers must be supported with information gathered from different chemical engineering books such as Perry's Chemical Engineering Handbook, the Unit Operations by McCabe, and the Transport Processes by Christie and Coplis. Okay, submit the solutions and answer until 5:30 today. Okay? If you have questions, do not hesitate to ask. Chat lang kayo ha. Okay, thank you and good day.